Just wanted to take a quick step through the project that I've been working on the last couple weeks, building a motor dyno. And I just got all the pieces kind of together and the first couple test runs done this last weekend. So I can finally actually really qualify a motor and record what kind of torque and power you get through the whole RPM range. So we're no longer stuck looking at props and worrying about what load and static or dynamic. So it's really just a basic torque arm dyno. I'm using an eddy current brake using discs out of hard drives. The brake is great because it's non-contact and very easily controllable, just driven off a servo. It doesn't look like much, but this thing can easily stall a motor at full power. And since I'm measuring the torque with the load cell on the stand, I don't need to be very specific with the braking. So it doesn't matter if the brake, that I don't know exactly how much force the brake is putting into it because I'm measuring the force at the motor. Driving the whole thing is my blade bench controller and acquisition board, same one that I use for my thrust stand. Only had to do minor rework to add the additional controls to it. The entire backside can slip backwards and forwards to adjust the motor position. The motor itself is mounted on a bearing just on its drive axis, and that pushes down on an off-the-shelf load cell. Here's a bit from the back. You can kind of see how the thing holds together. I originally did make a spider coupler for the drive, but my alignment wasn't tight enough, and I actually found that using the old tube trick worked a lot easier and handled the misalignment with a lot less trouble. Normal hobby servo drives the magnet arm of the current brake, and there you can see kind of the two discs in there, and I could very easily use only one if I needed to. At the very end of the shaft I've got markers and my fiber optic tack, just like I use on the thrust stand as well. This isn't the most ideal because it doesn't account for any slippage anywhere in the system, but it's a lot more convenient for early testing. This is what it looks like running a typical test program that I'm running right now. Give time for the motor to spin up and the tack to calibrate, and then spin it up to the target throttle speed, bring the current brake arm in, and start loading it down. Once the test is finished, the brake closes all the way to brake it to a complete stop, and then I've got a log that I can pull data from. The data that I'm getting off it looks like this. It's the same basic software stack that I used for a thrust stand, so all of my charting stuff I'm just using almost as is with only little changes to do the dyno. This is showing the RPM of that same test cycle that we just saw, and you can see I've got beautiful clean lines, and here each of these is a different throttle range, and you can see how much the brake can load it down. I'm only braking to about 50 or 60% throw on the current brake right now, and right now this is hitting full throttle. Here is like 24,000 RPM, and 50% throw on that is getting us just over 50% loading on the motor. So like I said, I can easily stall the motor if I want to, but trying to keep the loads down because especially at over 50% throttle, the motor heats up really quickly under this heavy load, and cycle times, you have to wait a long time in between for the thing to cool down. This is what the electrical power input looks. So this is voltage times amperage. And again, we get a beautiful stack up, and you can see just how much, even on this old crappy MT2204, you can see we're hitting almost 250 watts at full throttle, and half load. So this is a slightly lighter load than you'd have with a heavy tri-blade prop. At light loads, the difference in power, like it almost no load at all, there's significantly less, like not even 75 watts. So the range of power draw that you have between no load and higher loads, and the amount that it affects the throttle amount that you're at too. So if you're at only 10 or 20% throttle, the full load wattage is less than 50 watts for full load at 20% throttle there. But most importantly, we get a nice range across the entire, so it doesn't matter if you're if we're interested in low load at high throttle or high load at low throttle, we can pull that data and see what's going on. This chart is a measure of the mechanical output power, so this gives us the torque times the RPM, also shown in watts. And here's where things are a little not as great. It's a lot noisier and less consistent than the RPM or the power measurements. So I'm planning a bit of rework. So I need to redo the bearings so they're a little less crunchy and they can spin more freely. I need to make a spindle that's going to be a little lighter load that we'll see in the next chart how that affects things. And I want to slightly change the mechanical arrangement of the load cell and the torque arm to hopefully increase the amount of force on the load cell, because right now the force is really low. Like my test weight on the load cell is only like 320 gram that I typically use to calibrate all of my stuff for, and the full throttle torque that I'm getting off this old 2204 is like not even half of that amount of force. So the torque numbers that we're getting out of the motors are a lot lower, and I want to kind of make more use of the sensitivity of the load cell amplifier. And really the most important chart that I'm interested in here is the RPM versus torque versus efficiency, and this is the results of the same charts that we just saw. So you're seeing the amount of torque in Newton meters that it's putting out at different throttle ranges. So these are multiple. It's like 10%, 20%, 30%, and this is a full throttle run. And you can see how much like zero torque is like down here off the bottom of the chart. So even with the load, even with the current brake not applied at all, there's a large amount of drag in the system between the bearings and everything else. So like the no braking portion of the full throttle stuff is like over 2/3 of the amount of power you get out of basically idle. So I want to be able to reduce that load and see on the lower end, because the efficiency here is colored and I'm not able to read low enough to get that section where the efficiency starts to drop off again. So I'm missing that section below the sweet spot. I'm not sure how important that is. I'm gonna have to play with some real motors and get a sense. I don't know how much that's going to affect us. I haven't compared it with the torque requirements, torque curves of props or any of that stuff. I'm still kind of setting it up and dialing things in. But given that in these tests, I certainly expect our torque curve is going to be on the upper side of this. We're definitely going to be using more of the torque that's available. So all of the stuff that's kind of below this range, I don't know how useful it's really going to be to find out. But I want to be able to see it anyway, because if we're going to fully qualify the motor, we might as well fully qualify the motor. But that's where I'm at, trying to increase the repeatability, but I definitely have been getting sections of pretty decent repeatability to begin. Like these are two tests done at different times, stacked next to each other, and they're in slightly different ranges, I think a lot because of the difference in reading in the load cell, because you can see on the RPM side that the RPM is almost perfectly lines up. So working on that, but really encouraging results so far, and we should be able to tell a lot more about motors and get a better sense of what the different motors are going to be able to do, and we can ignore the props from the equation entirely, which I'm really excited about.